yesterday you had an assignment that was all about an object going, well, it was the cow falling. Who did the cow thing yesterday? All right, so with that, if you needed a little refresher on that, you've got your little cow on the top of the cliff. All right. Okay, and we're going to call this position 1 and this position 2. And the way you do this would be that you have the kinetic energy at 1 plus the potential energy at 1 equals the kinetic energy at 2 plus the potential energy at 2. This is an equation on your reference tables, and that is on the back. It says total energy is PE plus KE plus Q. We're ignoring Q simply because there's no friction involved. All right, so I'm just saying that KE plus PE equals KE plus PE at both of those, because that is the total energy, and the total energy doesn't change from one position to the other. Now at position 1, there is no kinetic energy because the cow isn't moving at all at that point, and kinetic energy is the energy of motion. All right, so I'm going to cross that out. And then when it falls down to the bottom and, goes down to the bottom, then there's no potential energy anymore because it's moved through that delta H distance. It's fallen down that delta H. This is delta H. Okay, so what you would just write is mg delta H, that's your potential energy, is equal to the kinetic energy, which is 1/2 mv squared. As you can see on the reference tables, PE is equal to that mg delta H, and KE is the 1/2 mv squared. So what happened is, in other words, way you can think about this is that the potential energy converted into kinetic energy. So you could find out how fast the cow was moving when it hit the ground or hit the car actually, because the mass cancels out and all you have left are the height in meters, little g from the reference table is 9.81 meters per second squared, and you can solve for v. Any questions? Pretty straightforward, right? So that's converting from a potential energy into a kinetic energy. And now we're going to look at an example that I'm going to make up off of the top of my head of, let's say we have a box, because in physics we always do boxes moving along, right? Let's say we have a box and it is, let's say it's 5 kilograms. Okay, and let's say the surface is wood. We're going to bring our friction in here. All right, and it's initially moving, VI, we'll say 15 meters per second. Okay, so we know we have some friction involved. So the question is, how far will this box slide before stopping? Okay, so when you have friction, you know that things heat up, right? If you put your hand together and you move back and forth, you're going to get some warmth from the friction. Friction, the heat that's happening, is actually internal energy. And if you look at the reference tables, we see that over on the right-hand side here, that Q is internal energy. Okay? Why is there a sound constantly going here? What's happening? Do I get that many emails? It must be. All right, so anyway, let's take a look and see what we've got. We're going to use our equation, the total energy equation. So we're going to say PE 1 plus KE 2. And sometimes we can write Q down, but well, I'll just write it down. It's a little weird to write that. I guess I write it like that. All right, the box is going to stop at some point. Okay? Stopping point. And this distance, D, we want to find out D. All right, so what is the potential energies at each point here? Does the potential energy change at all from one spot to the next? It doesn't really at all, right? There's no vertical change between the first position and the second position. I can label these two as position 1 and position 2. All right. Let me see here. Okay, so that means we can cross off potential energy 1 and potential energy 2. There's no change. Now there is kinetic energy, right? Because it's moving at the first position, but at the second position it stopped. So there's no kinetic energy there at all. Also, at least in our equation, in our problem, before it starts rubbing against the floor with some friction, right? There's no internal energy. The particles aren't really speeding up. So we're going to say that there's none right here. But there is some internal energy at the end. It's heated up. Okay? So our kinetic energy will be equal to the internal energy. And so let's write that. Let's write down the equation now, which is going to be 1/2 mv squared. But it turns out the internal energy that occurs is going to be equal to the work done by friction. All right? Remember, energy is simply the ability to do work. So you can think of the friction force as taking work away, or taking energy away from the box, because it stops, right? That energy has to go somewhere as internal energy. So the frictional force, we're going to say the frictional force times the stopping distance is the work. And we can solve for D because we can find out the frictional force. How do we find the frictional force? We use our friction equation off the reference tables right here. And we have our normal force, and we multiply it by our coefficient of friction, which is wood on wood, and it's kinetic friction because it's moving. Okay, so let's go and do that. So this is going to be equal to Fn times the coefficient friction times D. And we'll put our numbers in there now. Fn, what is Fn equal to? No. That's right, so it's mg. mg times ud, right? So if we look at this equality from all the way from the left to the right, which one cancels out? M, that's right, so we don't even need to know what that is. So our final equation will be 1/2 15 meters per second squared equals to 9.81 meters per second squared times 0.3 times D. And now we can solve for D. D! What is it? Whoa, that's big. Well, it is moving pretty quickly. Are you guys doing this for me too, please, so I make sure I do it right? I got 38.2 meters. So in all these problems that you have, you may not have some friction in these problems, but try to think logically. It's actually this energy stuff is actually very logical. You're converting from one to the other, and if there's friction, friction is taking away the energy, and it's equal to the work done by the friction. Right? So it's just like energy loss, and it's the work done, which is just the force times the distance. Okay, so it's very I don't want you to just memorize equations. Get a feel for what's happening, because it's all very common sense once you get to the common sense. Okay, so good luck on these questions, and if you have questions on them, I can give you leading questions to help you out instead of just telling you straight out. You can work together as well, collaboratively. All right.